The laws of the universe apply everywhere. This is the foundational assumption of physics. It is the principle that makes science possible. The gravitational constant does not change from one galaxy to the next. The speed of light is the same in every reference frame. The conservation laws hold in every process. The laws of the universe apply everywhere. In every laboratory on Earth, in every galaxy across the cosmos, in the cores of stars, in the spaces between galaxies, in the first fractions of a second after the earliest moments of cosmic history, in the interiors of neutron stars, in the hearts of particle accelerators. Everywhere we have ever looked, everywhere we have ever measured, everywhere we have ever pointed our instruments or our equations, the laws of physics hold. They are universal, they are consistent, they are unbroken. The speed of light is the same in every reference frame. The conservation of energy holds in every process. The uncertainty principle governs every quantum system. The laws of the universe apply everywhere. This is the foundational assumption of physics. It is the principle that makes science possible. The gravitational constant does not change from one galaxy to the next. The speed of light is the same in every reference frame. The conservation laws hold in every process. The laws of the universe apply everywhere, except in one place. The failure of the laws at the singularity is hidden behind the event horizon, sealed from observation. The universe has placed its most profound mystery behind an impenetrable barrier. The most important unsolved problem in physics occurs at a place that can never be directly observed. The clues to the solution must come from theory, from mathematical consistency, from the constants of information preservation and thermodynamics, and from the indirect observations of the exterior that constrain the possible form of the interior physics. At the center of every black hole, the laws of the universe no longer apply. The equations of general relativity, which describe gravity with extraordinary precision everywhere else, produce infinity. The curvature of spacetime diverges. The density diverges. The tidal forces diverge. Every quantity that the laws can compute produces a result that has no physical meaning. The mathematical language that describes reality with such precision everywhere else falls silent at this one point. The laws do not merely become difficult to apply. They do not merely produce approximate answers. They fail, completely, catastrophically. For the first time in the history of physics, the universe contains a place that its own laws cannot describe. The concept of universality, the idea that the same laws apply everywhere, is one of the deepest principles of science. The gravitational constant is the same on Earth as in a distant galaxy. The speed of light is the same in every reference frame. The charge of the electron is the same in every atom. The universality of the laws is what makes science possible, and the singularity is the exception, the one place where universality breaks, the one place where the laws reach their limit. The failure of the laws at the singularity is not a philosophical abstraction. It is a mathematical fact, proven by the Penrose-Hawking singularity theorems, established by the most rigorous methods of differential geometry and topology. The failure is guaranteed under very general conditions. It is robust against perturbation. It is unavoidable within the framework of general relativity. The laws guarantee their own failure. The Penrose-Hawking singularity theorems, proven through the most rigorous methods of differential geometry and topology, demonstrate that the failure is unavoidable under very general physical conditions. No amount of asymmetry or perturbation can prevent it. The failure is generic, robust, and mathematically airtight within the framework of general relativity. The equations, when applied to the extreme conditions at the center of a black hole, produce a result that is inconsistent with physical reality, infinity. The personal dimension of this failure is striking. If you fell into a supermassive black hole, the laws of physics would describe your journey with exquisite precision. Every tidal force, every visual distortion, every time dilation effect, right up to the final moment. And then, at the center, the laws would produce infinity. Your trajectory would terminate. Your world line would end. The laws that described your entire journey would, at the final destination, fail to describe what happens to you. The most important moment would be the most indescribable. This place is the singularity, and it exists at the center of every black hole in the universe. According to current scientific estimates, the observable universe contains on the order of 100 billion galaxies. Each one harbors at least one supermassive black hole and potentially hundreds of millions of stellar mass black holes. Our Milky Way has Sagittarius A star, with roughly 4 million solar masses. Messier 87 has one with roughly 6.5 billion solar masses. Every one of these objects contains a singularity. Every one contains a place where the laws of the universe no longer apply. The breakdown is not an isolated incident. It is a pandemic of lawlessness, occurring at billions of locations simultaneously, hidden behind event horizons, sealed away from the rest of the universe by the most impenetrable boundaries in nature. The existence of such a place raises the deepest questions in all of science. What does it mean for the laws of the universe to fail? Are the laws truly universal if they have exceptions? Is the failure a genuine feature of reality, or is it a signal that we are using the wrong laws? And what happens at the singularity, at the place where the laws no longer apply? What replaces the laws? What governs the physics in the absence of physics? By the end of tonight, you are going to understand what the singularity is, why the laws fail there, what the failure means for our understanding of the universe, and what the leading proposals for restoring the laws look like. You are going to confront the possibility that the laws we currently use are not the final laws, that the failure at the singularity is a signal pointing toward deeper, more fundamental laws that have not yet been discovered. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. The place where the universe's laws no longer apply is not merely a curiosity of theoretical physics. It is the most important unsolved problem in science. Because if the laws fail at the singularity, then our understanding of the universe is incomplete. The laws we have are not the final laws. The theory we have is not the final theory. Somewhere, waiting to be discovered, there exists a deeper set of laws, a more fundamental theory that applies everywhere, including the place where the current laws fail. Finding those laws is the central quest of modern theoretical physics. Now, let us begin. To understand the place where the universe's laws no longer apply, we must first understand the laws that fail. We must understand general relativity, its mathematical structure, its extraordinary successes, and the precise mechanism by which it produces the singularity. The failure is not random. It is precise, specific, and deeply connected to the fundamental assumptions of the theory. General Relativity was published by Albert Einstein in 1915. It describes gravity as the curvature of space-time caused by mass and energy. The mathematical framework is differential geometry on smooth manifolds. The central equations are Einstein's field equations, 10 coupled, nonlinear partial differential equations relating the geometry of spacetime to the distribution of mass and energy. The first exact solution was found by Karl Schwarzschild in 1916, while serving on the Eastern Front of the First World War and dying of a fatal autoimmune disease. His solution describes the spacetime around a non-rotating, uncharged spherical mass. At the Schwarzschild radius, an event horizon forms. At the center, a singularity forms, a point where the curvature invariants diverge, and the mathematical description of spacetime ceases to function. The mathematical structure of the failure deserves detailed attention. General relativity describes spacetime as a smooth manifold equipped with a metric tensor. The metric encodes the distances between nearby events, the angles between nearby directions, the relationship between space and time at every location. The curvature is derived from the metric through differentiation. The Riemann curvature tensor, which encodes the complete curvature information, has components that can be computed at every point of the manifold. At the singularity, the metric is not well defined. The curvature diverges. The smooth manifold structure terminates. The singularity is not a point of the manifold. It is the boundary of the manifold, the edge beyond which the mathematical description cannot be extended. The laws of general relativity, which are formulated on smooth manifolds, have no domain to operate in at the singularity. The laws do not merely give wrong answers, they have no territory to apply to. The concept of the photon sphere at 1.5 Schwarzschild radii illustrates the extreme curvature near the event horizon. At the photon sphere, light itself orbits the black hole. If you hovered there and looked straight ahead, you would see the back of your own head, the light having circled the black hole. The same curvature that produces these visual effects produces, at the center, the divergence that defines the place where the laws fail. The concept of the innermost stable circular orbit at 3 Schwarzschild radii for a non-rotating black hole marks the closest stable orbit. Inside this radius, matter must fall in or escape. The laws work perfectly at the innermost stable circular orbit. They describe the accretion dynamics, the X-ray spectra, the orbital mechanics. The laws continue to work through the event horizon. They fail only at the center. The Unruh effect connects the failure to acceleration. An accelerating observer in flat spacetime perceives a thermal bath. The Hawking temperature is the gravitational analog. The equivalence principle connects the two. The failure at the singularity is connected through these equivalences to the deepest quantum properties of the vacuum. The M-sigma relation shows that supermassive black holes and their host galaxies co-evolve. The growth of the black hole shapes the galaxy through feedback processes. The place where the laws fail is at the center of every large galaxy, connected to the evolution of cosmic structure through accretion and feedback. The concept of geodesic incompleteness provides the technical definition of the failure. In a smooth manifold without singularities, geodesics can be extended indefinitely. In a spacetime with a singularity, some geodesics terminate after finite affine parameter. They reach the singularity and stop. The spacetime is geodesically incomplete. The paths of freely falling particles end. The mathematical description has a boundary. The Kruskal-Sekeres coordinates provide the maximal analytic extension of the Schwarzschild spacetime. Even in this maximal extension, the singularity persists. The smooth manifold cannot be extended through it. The mathematics has been pushed to its absolute limit. The laws have no further reach. The Schwarzschild interior describes the geometry inside the event horizon. Space and time exchange their mathematical roles. The radial direction becomes time-like. The time direction becomes space-like. The singularity at the center is not a place in space but a moment in time, a future moment as inevitable as tomorrow. The laws describe this inversion with mathematical precision. The metric tensor changes the signs of its radial and temporal components. The light cones tilt inward until every possible future leads to the singularity. The laws describe the trap. They describe the inversion. They describe the inevitability. They fail only at the destination. The proper time from the event horizon to the singularity depends on the mass. For Sagittarius A star, roughly 20 seconds. For M87 star, possibly hours. During this time, the laws work perfectly, describing every tidal force, every curvature component, every geodesic. The laws succeed for the entire journey. They fail only at the end. The tidal forces inside the black hole grow as the singularity is approached. For a supermassive black hole, they start negligibly and build gradually. In the final moments, they exceed the binding energy of molecules, then atoms, then nuclei. The spaghettification of matter by extreme tidal forces is described perfectly by the laws. The forces are finite and calculable at every point except the singularity. For a rotating Kerr black hole, the interior is more complex. 2 horizons, a ring singularity, the mass inflation instability at the inner Cauchy horizon discovered by Werner Israel and Eric Poisson. The Kerr mathematics permits paths through the ring singularity into different spacetimes, but the inner horizon is almost certainly unstable. The real interior of a rotating black hole is messier and less understood than the idealized picture. The failure of the laws inside a rotating black hole is more complex but no less absolute. The Schwarzschild radius depends only on mass. For our Sun, roughly 1.86 miles. For Sagittarius A star, roughly 7.5 million miles. For M87 star, roughly 12 billion miles. The event horizon is not where the laws fail. The laws work perfectly at the event horizon. The failure occurs only at the center, at the singularity. at the mathematical point of zero radial distance where every curvature variant diverges. The laws of physics, as encoded in general relativity, have been tested with extraordinary precision outside the singularity. The global positioning system relies on general relativistic corrections to maintain accuracy. Without these corrections, GPS positions would drift by roughly 10 kilometers per day. Every smartphone, every car navigation system, every aircraft guidance computer depends on the laws of general relativity working perfectly. The LIGO Observatory has detected roughly 90 gravitational wave events from merging black holes and neutron stars. Each waveform matches the predictions of general relativity with remarkable precision. The Event Horizon Telescope has photographed the shadows of M87 star and Sagittarius A star. The shadows match the predictions. Andrea Ghez and Reinhard Genzel shared the Nobel Prize in 2020 for tracking stars orbiting Sagittarius A star for more than 2 decades. Every orbit matches. The relationship between the failure and the concept of the cosmic censorship conjecture provides the framework for understanding the quarantine. Roger Penrose proposed in 1969 that singularities formed by collapse are always hidden behind event horizons. If cosmic censorship holds, the failure is always sealed away. The outside universe never sees the infinite curvature. The lawlessness is hidden from the law-abiding exterior. But cosmic censorship has never been proven in full generality. Its truth or falsity remains one of the great open problems in mathematical physics. If cosmic censorship fails, naked singularities could form, and the place where the laws fail could be visible to the outside universe. The failure would be exposed. The lawlessness would be public. The concept of the M-sigma relation shows that the growth of supermassive black holes and their host galaxies are linked. The mass of the central black hole correlates with the velocity dispersion of stars in the galactic bulge. The place where the laws fail, at the center of the black hole, has shaped the evolution of its host galaxy through feedback processes. The failure at the center has cosmic scale consequences. The laws work everywhere except at one point. The Kretschmer scalar, a coordinate-independent measure of spacetime curvature, is proportional to the mass squared divided by the 6th power of the radial distance for a Schwarzschild black hole. As the radial distance approaches zero, the Kretschmer scalar diverges to infinity. This divergence is present in every coordinate system. It cannot be removed by any change of variables. It is a genuine feature of the geometry. The laws produce infinity at the center. The Penrose-Hawking singularity theorems, proven in the mid-1960s, established that the failure is not an artifact of the Schwarzschild solution's perfect symmetry. Roger Penrose proved in 1965 that singularities are unavoidable under very general conditions. The proof requires only that general relativity is correct, that energy density is positive, and that a trapped surface has formed. Stephen Hawking extended the methods. Together they established that the singularity is generic, robust, and unavoidable within the framework of general relativity. Penrose shared the Nobel Prize in 2020. The concept of the gravitational wave observations from the LIGO-Virgo-Cagra collaboration provides the most precise tests of the laws outside the place where they fail. Roughly 90 events have been detected. Each waveform matches the predictions of general relativity with extraordinary precision. The chirp mass, the spin parameters, the ring-down frequencies, all match numerical solutions of Einstein's equations. The ring-down phase, when the merged black hole vibrates and settles into its final state, tests the no-hair theorem. Every observation confirms that the laws work perfectly outside the singularity. The contrast between the extraordinary precision outside and the complete failure inside could not be more stark. The laws fail under the most general circumstances, not because of special symmetry, not because of idealized conditions. Under the most general, most realistic, most physically relevant conditions, the laws produce infinity. The place where the laws no longer apply is not a mathematical artifact. It is a mathematical necessity. The density at the singularity is predicted to be infinite. For a stellar mass black hole of 10 solar masses, this means 20,000 billion kilograms compressed into zero volume. The density of a neutron star, the densest stable object we can observe, is roughly 500 million tons per cubic centimeter. The Planck density, where quantum gravitational effects are expected to dominate, is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. The gap between neutron star density and the Planck density spans roughly 78 orders of magnitude. The gap between the Planck density and the singularity's infinite density is itself infinite. The tidal forces at the singularity are infinite. The Riemann curvature tensor, which encodes the complete curvature information, diverges. The geodesics, the paths of freely falling particles, terminate. The spacetime is geodesically incomplete. The smooth manifold has a boundary beyond which it cannot be extended. The laws have reached their limit. The mathematical description stops. The concept of the trapped surface deserves emphasis in the context of the failure. A trapped surface is a closed surface from which all outgoing light rays converge inward. Inside the event horizon, every sphere is trapped. The existence of a trapped surface guarantees, within general relativity, the existence of the singularity. The laws produce the conditions that guarantee their own failure. The Penrose diagram makes this visual. The interior is diamond-shaped, bounded by the horizon below and the singularity above. Every future-directed path ends at the singularity. The laws describe every path. The laws fail at every destination. The diagram is the most concise summary of the relationship between the laws and the failure. The laws govern every step of the journey, and the journey always ends where the laws fail. The concept of the Cauchy horizon in a rotating Kerr black hole adds complexity. The Cauchy horizon is the inner boundary beyond which the laws of general relativity cannot uniquely determine the future. The mass inflation instability demonstrated by Israel and Poisson shows that the Cauchy horizon is replaced by a singularity in realistic scenarios. The failure of the laws inside a rotating black hole is more complex but equally absolute. The strong cosmic censorship conjecture states that the Cauchy horizon is always singular, preventing the extension of the spacetime beyond it. Recent work in de Sitter spacetimes has found possible violations. If the conjecture fails, the region beyond the Cauchy horizon is genuinely indeterminate. The laws cannot predict what happens. The failure extends from producing infinity at the singularity to producing indeterminacy beyond the Cauchy horizon. The concept of the trapped surface is central to the Penrose theorem. A trapped surface is a closed two-dimensional surface from which all outgoing light rays converge inward. Inside the event horizon, every sphere is a trapped surface. The existence of a trapped surface, combined with positive energy and the validity of general relativity, guarantees geodesic incompleteness. The laws guarantee their own failure. The connection between the failure and the concept of gravitational waves provides observational context. Each gravitational wave detection by the LIGO-Virgo-Cagra collaboration tests general relativity in the strong field regime. The ring-down signals from black hole mergers test the no-hair theorem. Roughly 90 events have been detected. Each confirms the laws outside the singularity. None reveals the laws at the singularity directly. The connection between the failure and the concept of the Roche limit provides a familiar analogue. The Roche limit is the distance at which tidal forces exceed the self-binding of an object. Saturn's rings are within the Roche limit. Near a black hole, every object has its own Roche limit. The tidal disruption that occurs at the Roche limit is governed by the same laws that fail at the singularity. The laws work perfectly at the Roche limit. They fail only at the center. The concept of gravitational time dilation shows how the laws produce extreme but finite effects near the event horizon. Time slows down relative to a distant observer. At the horizon, time stops from the outside perspective. The laws describe this extreme effect perfectly. They produce finite, well-defined, physically meaningful predictions. Only at the center do they produce infinity. The visual experience near a black hole has been computed by numerical ray tracing. The outside universe appears compressed into a shrinking bright disk. Below, darkness. Multiple images appear at different positions. The visual distortions are described perfectly by the laws. The beauty of the images and the failure at the center are products of the same equations. The concept of frame dragging in a Kerr spacetime adds complexity. A rotating black hole drags spacetime with it. In the ergosphere, nothing can remain stationary. The laws describe the frame dragging perfectly. They describe the Penrose process for extracting energy. They fail only at the ring singularity at the center. The observational evidence for the precision of the laws everywhere except at the singularity is overwhelming. The binary pulsar PSRB 1913+16, discovered by Russell Hulse and Joseph Taylor in 1974, provided the first confirmation of gravitational wave emission. The orbital decay matched general relativity to better than 1/3 of 1%, earning Hulse and Taylor the Nobel Prize in 1993. The LIGO detection of gravitational waves from merging black holes in 2015 tested general relativity in the strong field regime. The waveforms matched numerical solutions of Einstein's equations with extraordinary precision. The chirp mass, the spin parameters, the ring-down frequencies all matched. The ring-down phase tests the no-hair theorem, confirming that the final merged black hole is consistent with the Kerr solution. The Event Horizon Telescope photographs confirmed the existence of event horizons. The shadow of M87 star matched the predicted size and shape. The shadow of Sagittarius A star, despite the variability of the source, also matched. The laws work perfectly at the event horizon. They fail only at the center. The four laws of black hole mechanics, established by James Bardeen, Brandon Carter, and Stephen Hawking in the early 1970s, mirror the four laws of thermodynamics. The zeroth law says surface gravity is constant. The first law relates mass, area, angular momentum, and charge. The second law says area never decreases classically. The third law says surface gravity cannot be reduced to zero in finite steps. These laws, derived from general relativity, constrain the failure at the singularity. Any replacement laws must reproduce these thermodynamic properties. The tidal disruption of stars by supermassive black holes has been observed dozens of times. Each event confirms the physics of extreme tidal forces predicted by general relativity. The light curves, spectra, and temporal evolution match numerical simulations. The laws work perfectly for the tidal disruption of stars. They fail only at the center, where the disrupted matter ultimately arrives. The connection between the failure and the concept of quantum field theory in curved spacetime provides the bridge between general relativity and quantum mechanics at the boundary of the failure. Quantum field theory on a curved spacetime background describes the behavior of quantum fields in the presence of gravity. The Hawking radiation is computed within this framework. The Casimir effect, the Schwinger effect, the particle creation by expanding spacetimes, all are described by quantum field theory in curved spacetime. But the framework assumes a smooth classical spacetime background. At the singularity, the background is not smooth, it is singular. The framework fails. Quantum field theory in curved spacetime is a semi-classical approximation, valid when the spacetime is well defined. At the singularity, the approximation breaks down. The laws of quantum field theory in curved spacetime join the laws of general relativity in failing at the place where the curvature diverges. The concept of the vacuum energy near the singularity illustrates this failure. The expectation value of the stress-energy tensor of quantum fields diverges near the singularity. The quantum vacuum, which is well-defined and finite everywhere else, becomes ill-defined at the singularity. The quantum laws and the classical laws fail together at the same point for related reasons. The concept of the Planck density provides the natural cutoff. At the Planck density, the semi-classical approximation breaks down. The quantum fluctuations of the geometry become comparable to the geometry itself. Space-time becomes quantum, foamy, uncertain. The smooth manifold that both general relativity and quantum field theory require ceases to exist. New laws, the laws of quantum gravity, must take over. The Hawking radiation, discovered in 1974, connects the failure to quantum mechanics. The radiation is thermal, with a temperature inversely proportional to mass. For a solar mass black hole, the temperature is roughly 60 billionths of a Kelvin. The evaporation time is roughly 10 to the power of 67 years. The radiation creates the information paradox. If the black hole evaporates completely and the radiation is thermal, information is destroyed. The laws of quantum mechanics, which require unitarity, are violated by the failure of the laws at the singularity. The Strominger-Vafa counting of 1996 provided the first microscopic counting of the Bekenstein-Hawking entropy within string theory. For certain extremal black holes, the microstate count matches the entropy formula exactly. The place where the laws fail has genuine microscopic quantum states. The failure is not a void, it is a place of enormous but hidden complexity. The event horizon seals the failure away. The cosmic censorship conjecture, proposed by Penrose in 1969, states that singularities formed by collapse are always hidden behind event horizons. If cosmic censorship holds, the place where the laws no longer apply is always quarantined, sealed behind the one-way boundary of the event horizon. The universe's lawlessness is hidden from the law-abiding exterior. The Kerr solution, found by Roy Kerr in 1963, describes a rotating black hole. The interior is more complex. Two horizons, a ring singularity, the mass inflation instability at the inner Cauchy horizon. The laws fail differently inside a rotating black hole, but they still fail. The singularity is a ring rather than a point. The curvature diverges at the ring. The laws produce infinity. The BKL dynamics, named after Belinsky, Kalatnikov, and Lifshitz, describe how the geometry behaves near a generic singularity. Space contracts in one direction while expanding in another, switching patterns with increasing frequency. Charles Misner called this mixmaster dynamics. Near the singularity, the laws of general relativity still apply, producing well-defined but increasingly extreme predictions until the very center, where they produce infinity and cease to function. The precision of the laws everywhere else makes the failure at the singularity all the more striking. The same equations that predict gravitational waves to extraordinary accuracy produce infinity at the center. The same tensor calculus that describes the curvature of spacetime around a binary pulsar produces a curvature that diverges at the singularity. The most precise mathematical framework in the history of science fails at one specific point. The place where the universe's laws no longer apply is the most precisely identified location in all of physics. The relationship between the event horizon and the singularity illustrates the precision of the failure. The laws work perfectly at the event horizon. They describe the time dilation, the light bending, the tidal forces, the causal structure with mathematical exactness. The laws continue to work inside the event horizon. They describe the inversion of space and time, the contracting geometry, the growing tidal forces. The laws work perfectly right up to the singularity, producing finite, well-defined, physically meaningful predictions at every point except one. The failure is not gradual, it is instantaneous. The transition from perfect precision to complete failure occurs at a single mathematical point. The concept of the proper time from the event horizon to the singularity emphasizes the brief duration between the domain of working laws and the failure. For Sagittarius A star, roughly 20 seconds. For M87 star, possibly hours. During this time, the laws work flawlessly. Then, at the center, they fail. The journey from working laws to failing laws takes seconds or hours, depending on the mass. The concept of the BKL dynamics describes the final approach to the failure point. The geometry oscillates chaotically. The Kastner exponents oscillate. The mixmaster dynamics churn space-time with increasing violence. The laws describe these oscillations with precision. The failure occurs at the endpoint of the oscillations, at the singularity itself. But what scientists discovered next was worse than anyone expected. The connection between the failure and the concept of the entropy of the universe provides cosmological perspective. The total entropy of all black holes is estimated at roughly 10 to the power of 104, vastly exceeding the entropy of all non-black hole matter at roughly 10 to the power of 88. The places where the laws fail contain the overwhelming majority of the universe's entropy. The failure is not a minor footnote to the cosmic entropy budget. It is the dominant term. The connection between the failure and the concept of the arrow of time adds temporal weight. The second law of thermodynamics says entropy never decreases. The arrow of time points in the direction of increasing entropy. The arrow points toward black holes, toward the places where the laws fail. The failure is the thermodynamic destination of the universe, the endpoint of entropy production. the place where disorder is maximized and the arrow reaches its target. The density at the event horizon provides perspective on the scales involved. For a stellar mass black hole, the density at the horizon is roughly 200 million tons per cubic centimeter. For Sagittarius A star, roughly 1,000 kilograms per cubic centimeter. For M87 star, less than the density of air. The failure at the center involves densities beyond the Planck density, beyond any meaningful physical comparison. The gap between the horizon density and the singularity density is infinite, containing within it the entire transition from the domain where the laws work to the domain where they fail. The formation of black holes through stellar collapse connects the failure to astrophysics. When a massive star exhausts its nuclear fuel, the core collapses. If the remnant exceeds roughly 3 solar masses, a black hole forms. A new instance of the place where the laws fail is created. This process has occurred billions of times throughout cosmic history. The concept of the Penrose diagram makes the relationship between the laws and the failure visually explicit. The interior appears as a diamond-shaped region bounded by the horizon and the singularity. Every future-directed world line from inside must reach the singularity. The laws govern every moment of the journey. They fail only at the destination. The core problem is not simply that the laws of general relativity fail at the singularity. Failures have occurred before in the history of physics. Classical electromagnetism fails at the atomic scale. Newtonian mechanics fails at the speed of light. In each case, the failure was resolved by a new theory with a broader domain of validity. Quantum mechanics replaced classical mechanics. Special relativity replaced Galilean relativity. The failure was a signal, a signpost pointing toward deeper laws. But the failure at the singularity is qualitatively different from every previous failure. It is worse, and understanding why it is worse is essential to understanding the place where the universe's laws no longer apply. The concept of the holographic principle transforms the understanding of the failure. If the three-dimensional interior is a holographic projection of two-dimensional boundary physics, then the failure at the singularity is a failure of the projection, not of the fundamental physics. The boundary theory has no singularity. The two-dimensional laws never fail. The failure is in the translation from 2 dimensions to 3 dimensions. The AD-SCFT correspondence, discovered by Maldacena in 1997, makes this precise. The boundary theory is a conformal field theory, well-defined, unitary, and finite. The bulk theory is general relativity, with its singularity and its failure. The two are equivalent. The failure in the bulk corresponds to something smooth and finite in the boundary. The laws of the boundary theory apply everywhere, including the point that corresponds to the singularity. The error-correcting structure of the holographic encoding provides the mechanism. The bulk geometry is encoded redundantly in the boundary. Away from the singularity, the code is robust and the geometric laws apply. Near the singularity, the code degrades. At the singularity, it fails. The geometric description loses coherence. But the boundary state, the fundamental description, continues to evolve smoothly. The island formula connects the boundary description to the evaporation process. Quantum extremal islands, regions of the interior that belong informationally to the radiation, grow during evaporation. The information is transferred from the failing bulk description to the well-defined boundary description. The laws of information preservation operate through the island mechanism, independent of the failure of the geometric laws. The page curve is reproduced. Information is preserved. The laws of quantum information are the laws that survive the failure. The laws of geometry are the laws that fail. The distinction between the laws that fail and the laws that survive is the most important insight about the place where the laws no longer apply. The first reason it is worse is that both of our greatest theories fail simultaneously. General relativity fails because it produces infinite curvature. But quantum mechanics also fails because it requires a smooth spacetime background on which to operate, and at the singularity, the background is not smooth. It is singular. The Schrödinger equation evolves the quantum state in time, but time itself is not well defined at the singularity. The quantum fields defined on a smooth manifold but the manifold has a boundary at the singularity. Both frameworks fail at the same point for related but distinct reasons. The non-renormalizability of general relativity makes the failure deeper than any previous one. When physicists try to quantize general relativity using the perturbative methods that work for the other forces, each order of perturbation theory introduces new types of infinities. The number of free parameters grows without bound. The theory loses predictive power. The mathematical framework of perturbative quantum field theory, which has been spectacularly successful for electromagnetism, the weak force, and the strong force, fails for gravity. The accretion process provides context for how matter reaches the place where the laws fail. Gas and dust spiral inward through accretion disks, heated by friction to millions of degrees. The disk can outshine an entire galaxy. Up to roughly 40% of the rest mass energy is radiated before the matter crosses the event horizon. After crossing, the matter falls toward the singularity, toward the place where the laws no longer apply. Every atom that has ever crossed an event horizon has reached, or will reach, the place where the laws fail. The Blandford-Zanajek process shows how magnetic fields threading the ergosphere of a rotating black hole can extract rotational energy and launch relativistic jets extending hundreds of thousands of light years. These jets, the most powerful sustained energy sources in the universe, are powered by the region just outside the place where the laws fail. The failure at the center is surrounded by the most energetic phenomena in the cosmos. The no-hair theorem states that a black hole is described by just three quantities: mass, charge, and spin. All other information is hidden behind the event horizon. The gap between the 3-number exterior and the 10 to the 77 state interior is the information gap. The failure of the laws at the singularity is connected to this gap. The laws cannot describe the enormous internal complexity with only 3 exterior parameters. The membrane paradigm, developed by Kip Thorne and collaborators, describes the event horizon as a physical membrane with viscosity, conductivity, and temperature. The membrane processes information, absorbs matter, and radiates. The stretched horizon, 1 Planck length, outside the mathematical event horizon, is the boundary between the domain where the laws work and the domain where they begin to fail. The connection between the failure and the concept of quantum entanglement provides one of the deepest perspectives. The smooth vacuum at the event horizon is maintained by entanglement between modes inside and outside. The Hawking radiation arises from the separation of entangled pairs. The information paradox arises because the entanglement structure cannot simultaneously satisfy unitarity and the smooth horizon. The firewall paradox shows that the entanglement may break at the horizon of an old black hole. If entanglement generates spacetime, as Van Ramsdonk showed, the place where the laws fail is the place where the entanglement structure can no longer support a smooth geometric description. The failure of the geometric laws is the failure of the entanglement to generate a coherent geometry. The fundamental entanglement laws continue to operate. The derived geometric laws do not. The concept of quantum complexity connects the failure to computation. The interior grows because quantum complexity increases. At the singularity, complexity exceeds geometric capacity. The geometric laws fail. The computational laws continue. The failure is a capacity limit, not a fundamental limit. The concept of the ER equals EPR conjecture connects the failure to quantum entanglement. Every pair of entangled particles is connected by a microscopic wormhole. The interior of the black hole is threaded with wormholes connecting it to the exterior through entanglement. The place where the geometric laws fail is connected to the exterior through quantum correlations. The failure is not a disconnection. It is a point where the geometric description fails, but the quantum connections persist. The concept of the Landauer principle connects the failure to thermodynamics at the most fundamental level. The Landauer principle states that erasing one bit of information produces a minimum amount of heat equal to the temperature times the natural logarithm of 2 times Boltzmann's constant. If information is destroyed at the singularity, the Landauer principle is violated. The connection between information and energy is disrupted at the place where the laws fail. The concept of the no-hair theorem highlights the information gap at the failure point. The exterior is described by three numbers: mass, charge, and spin. The interior has 10 to the power of 77 microstates. The place where the laws fail is the place where this enormous hidden complexity resides. The failure of the geometric laws at the singularity is connected to the inability of geometry to describe 10 to the power of 77 microstates with only three parameters. The relationship between the failure and the concept of vacuum fluctuations provides quantum context. The quantum vacuum is not empty. It is filled with zero-point fluctuations, virtual particles constantly created and annihilated. Near the event horizon, these fluctuations are modified by the extreme curvature, producing the Hawking radiation. Near the singularity, the vacuum structure is unknown because the background spacetime on which quantum field theory is defined has broken down. The place where the laws fail is also the place where the quantum vacuum is undefined. The concept of quantum complexity adds dynamics. The interior grows because quantum complexity increases. The geometric laws describe this growth. At the singularity, complexity exceeds geometric capacity. The geometric laws fail. The computational laws continue. The failure is a capacity limit of the geometric language. The concept of the Wheeler-DeWitt equation connects the failure to the problem of time. The equation has no time variable. Time is emergent. The failure of time at the singularity is the failure of an emergent quantity. The timeless fundamental state continues. The time-dependent geometric laws fail. The concept of the Weyl curvature hypothesis connects the failure to the arrow of time. The initial singularity has low Weyl curvature. The black hole singularity has high Weyl curvature. The failure at the black hole singularity is the endpoint of gravitational entropy production. The arrow of time points toward it. The concept of the Planck star provides the concrete resolution within loop quantum gravity. The singularity is replaced by a Planck density core. The laws of discrete quantum geometry govern this core. The geometric laws fail. The quantum geometric laws succeed. The place where the old laws fail is the place where the new laws produce their most dramatic prediction, the quantum bounce. The Bekenstein bound sets the maximum information content. Black holes saturate it. The Margulis-Levitin theorem sets the maximum processing speed. Black holes saturate it. The place where the laws fail is the place of maximum quantum activity, maximum information density, maximum processing speed, maximum entropy production. The Chandrasekhar limit, roughly 1.4 solar masses, is the maximum mass of a stable white dwarf. The Oppenheimer-Volkoff limit, roughly 3 solar masses, is the maximum mass of a stable neutron star. Above this limit, no known force can prevent collapse past the Schwarzschild radius. The formation of a black hole and the creation of the place where the laws fail is the inevitable consequence of stellar evolution for the most massive stars. And it gets worse. The failure at the singularity is not merely a failure of prediction. It is a failure of description. The laws do not merely give wrong answers at the singularity. They give no answers. The mathematical framework ceases to function. The smooth manifold terminates. The equations have no domain to operate in. The laws do not merely break down. They cease to exist as meaningful mathematical statements. The information paradox, discovered by Stephen Hawking in 1974, reveals that the failure extends beyond the singularity to the event horizon itself. Hawking showed that black holes emit thermal radiation. The radiation carries no information about what fell in. If the black hole evaporates completely, all information is permanently destroyed. Unitarity, the quantum mechanical principle that information is always preserved, is violated. But here is the problem. Unitarity is not a law that can be casually discarded. It is the mathematical structure that ensures the consistency of quantum mechanics. If unitarity fails, probabilities can leak. They can add up to more or less than 1. The predictions of quantum mechanics become inconsistent. The failure at the singularity causes a cascading failure in quantum mechanics, threatening the consistency of the entire theoretical framework. Most physicists now believe information is preserved. Hawking himself conceded his bet with John Preskill in 2004. The island formula, developed in 2019 and 2020, confirm that the entropy of Hawking radiation follows the Page curve, the mathematical signature of unitary evolution. Information is preserved, but the mechanism of preservation remains unclear. The place where the laws no longer apply is the place where the information should be destroyed. If the information survives, the laws must be different at the singularity from what general relativity predicts. Different laws must apply. Laws that we have not yet discovered. The firewall paradox, introduced in 2012 by Ahmed Almheiri, Donald Marolf, Joseph Polchinski, and James Sully, showed that the conflict extends to the event horizon. 3 principles: unitarity, the equivalence principle, and the validity of quantum field theory, cannot all hold simultaneously at the horizon of an old black hole. At least one must fail. The place where the laws no longer apply may extend from the singularity to the horizon itself. The Bekenstein-Hawking entropy, proportional to the area of the event horizon, tells us that the black hole has an enormous number of microscopic quantum states. For a solar mass black hole, roughly 10 to the power of 77. The no-hair theorem says the exterior is described by just 3 numbers. The interior has 10 to the power of 77 microstates. The gap between 3 exterior parameters and 10 to the power of 77 interior states is the information gap. At the place where the laws no longer apply, this gap reaches its maximum. The scrambling time, the time for the black hole to process infalling information, is milliseconds for Sagittarius A star. The Margulis-Levitin theorem sets the maximum speed of quantum evolution. Black holes saturate this bound. The place where the laws no longer apply is also the place of maximum quantum activity, operating at the absolute physical limit of information processing. The concept of the Strominger-Vafa counting provides concrete evidence that the place where the laws fail has genuine microscopic structure. For certain extremal black holes, the microstate count within string theory matches the Bekenstein-Hawking entropy exactly. The place of failure has countable quantum states. The failure is not a void. It is a place of enormous but hidden complexity, with 10 to the power of 77 microstates for a solar mass black hole. The concept of the Hayden-Preskill protocol shows that information entering the place where the laws fail is not permanently trapped. Individual quantum bits can be recovered from the Hawking radiation after one scrambling time, milliseconds for Sagittarius A star. The failure of the geometric laws does not mean the failure of information recovery. The new laws preserve and return the information. Something is wrong with our assumptions about the nature of spacetime at the most fundamental level. The assumption that spacetime is a smooth, continuous manifold, the assumption on which both general relativity and quantum field theory are built, must be wrong at the Planck scale. The place where the laws no longer apply is the place where this assumption breaks. The failure is not in the laws. The failure is in the assumption on which the laws are built. The BKL dynamics near the singularity describe how the geometry oscillates chaotically in the approach to the failure point. The Kasner exponents describe the rates of the contraction and expansion along 3 spatial directions. The exponents oscillate chaotically, each epoch leading to the next through the BKL map. The Lyapunov exponents are positive, meaning the dynamics are chaotic. The approach to the place where the laws fail is not smooth but turbulent, a violent geometric convulsion that accelerates without bound. The connection between the failure and the concept of the cosmological constant problem adds scope. Both problems involve the behavior of quantum fields in extreme gravitational environments. Both involve the Planck scale. Both require quantum gravity. The failure at the singularity may be connected to the mystery of why the vacuum energy is roughly 120 orders of magnitude smaller than the quantum field theoretic prediction. The connection between the failure and the concept of determinism is important. If the singularity exists, geodesics terminate. The future cannot be predicted beyond the termination point. Determinism fails. The laws of physics not only produce infinity at the singularity, but also lose the ability to predict the future. The place where the laws fail is also the place where predictability fails. The strong cosmic censorship conjecture states that the interior beyond the Cauchy horizon of a rotating black hole is indeterminate. Recent work in de Sitter spacetimes has found that this conjecture may be violated. If so, the place where the laws fail may extend beyond the singularity to include regions of genuine indeterminism. The concept of the BKL dynamics and provides the detailed poise picturation of the approach to the failure. The Kästner exponents oscillate chaotically. The approach is not smooth but turbulent. The laws describe this turbulence with precision, producing well-defined but chaotic predictions. Only at the singularity itself do the laws produce infinity and cease to function. The concept of the Mixmaster universe, introduced by Misner, describes the chaotic oscillations near the singularity as a cosmological process. The interior of the black hole near the singularity is mathematically equivalent to a contracting, chaotically oscillating universe. The laws describe this contracting universe. They fail only at the final moment of the contraction. The Mixmaster dynamics, as Misner called them, mean that the failure at the singularity is preceded by a chaotic prelude. The geometry of spacetime is churned, twisted, and distorted with increasing intensity and frequency. The laws of general relativity describe this prelude with precision, producing well-defined but extreme predictions for the chaotic oscillations. Only at the singularity itself, at the endpoint of the prelude, do the laws fail. The connection between the proposals and the concept of emergent spacetime deserves detailed attention. If spacetime is emergent, the geometric laws are derived laws. They apply in the domain where the emergence is successful. They fail where the emergence breaks down. The singularity is the point of maximum emergence failure. The fundamental laws from which spacetime emerges continue to operate. Mark van Ramsdonk showed that entanglement generates spacetime. Near the singularity, the entanglement structure is maximally disrupted. The emergent spacetime reaches its most extreme, most distorted, most hostile configuration. The geometric laws fail because the entanglement can no longer support a coherent geometry. The error-correcting code of holographic spacetime provides the mechanism. The bulk geometry is encoded redundantly. The code protects the geometric description from local errors. Near the singularity, the code degrades beyond repair. The geometric description collapses. The boundary state, the fundamental description, survives. The Ryu-Takayanagi formula connects entanglement on the boundary to geometry in the bulk. The quantum version leads to the island formula. These formulas are the mathematical bridge between the laws that work, boundary quantum mechanics, and the laws that fail, bulk geometry. The bridge itself is a law that connects the two domains. The gravitational path integral sums over all geometries, including replica wormholes. The sum produces finite, unitary answers. The singularity, present in individual geometries, is washed out in the quantum sum. The laws of the full quantum theory have no place where they fail. The failure is an artifact of restricting to classical geometries. The computational complexity perspective adds temporal dynamics. The interior grows with complexity. At the singularity, complexity exceeds geometric capacity. The geometric laws fail. The computational laws continue. The failure is a capacity limit of one language, not a failure of all languages. The proper time from the event horizon to the singularity determines how long the laws work before they fail. For Sagittarius A star, roughly 20 seconds. For M87 star, possibly hours. During this time, the laws work perfectly, describing every tidal force, every curvature component, every geodesic deviation. The laws succeed for the entire journey and fail only at the destination. The visual experience of the approach has been computed numerically. The outside universe appears compressed into a shrinking bright disk above. Below, darkness. Multiple images of distant stars appear at different positions. The visual field evolves continuously. The beauty of the visual distortions is described perfectly by the laws. The terror at the destination is where the laws fail. The density gradient during the fall provides perspective. Near the horizon of a supermassive black hole, the density is comparable to air. As you fall deeper, the curvature increases. Near the singularity, every quantity diverges. The transition from gentle to extreme occurs during the fall. The transition from law to lawlessness occurs at the center. The Heisenberg uncertainty principle provides the most direct argument that the classical singularity cannot exist. If matter is compressed to zero volume, position is known exactly. But the uncertainty principle says infinite precision in position requires infinite uncertainty in momentum, infinite kinetic energy, and infinite pressure resisting further compression. Quantum mechanics forbids the singularity. The place where the laws of general relativity no longer apply is the place where the laws of quantum mechanics demand something different. The Planck scale marks the boundary between the domain where the current laws apply and the domain where they do not. The Planck length, roughly 10 to the power of negative 35 meters. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. The Planck time, roughly 10 to the power of negative 43 seconds. At these scales, both general relativity and quantum field theory are expected to fail. The place where the laws no longer apply begins at the Planck scale. The connection between the failure and the concept of the four laws of black hole mechanics provides thermodynamic constraints. The zeroth law says surface gravity is constant. The first law relates mass, area, angular momentum, and charge. The second law says area never decreases. The third law says surface gravity cannot be reduced to zero. These thermodynamic properties of the exterior constrain the failure at the interior. Any replacement laws must reproduce these thermodynamic relationships. The exterior thermodynamics is finite and well-defined. The interior must be compatible. The infinite failure is thermodynamically incompatible with the finite exterior. The gap between the Planck scale and our experimental capabilities is roughly 17 orders of magnitude. The physics of the place where the laws no longer apply must be determined through theory alone, constrained by the information paradox, the holographic principle, the thermodynamics of black holes, and the requirement of mathematical consistency. The concept of the stretched horizon connects the failure to the quantum boundary. The stretched horizon, one Planck length outside the event horizon, has temperature, entropy, and viscosity. It processes information. It is the physical realization of the quantum degrees of freedom. The laws of the stretched horizon are quantum laws, well-defined and finite. The failure occurs deeper, at the singularity, beyond the stretched horizon. The concept of black hole complementarity means the failure looks different to different observers. The outside observer sees information processed on the stretched horizon. No failure, no singularity, no lawlessness. The falling observer sees the interior and the approach to the singularity, the failure, the lawlessness. Both descriptions are valid. The failure is observer-dependent. The concept of the page curve provides the definitive test of information preservation through the failure. Rising entropy during the first half of evaporation. Falling entropy during the second half. The island formula reproduces this curve. Information survives the failure. The laws of information preservation are not the laws that fail. The four laws of black hole mechanics constrain any replacement laws. The new laws must reproduce the Bekenstein-Hawking entropy, the Hawking temperature, and the thermodynamic relationships. The constraints are severe. The new laws are not arbitrary. They are tightly constrained by the thermodynamics of the object that contains the failure. The connection between the failure and the concept of gravitational waves provides observational context for the regime approaching the failure. Each gravitational wave detection tests general relativity in the strong field regime, near the boundary where the laws are most strained. The ring-down signals from black hole mergers test the no-hair theorem. Future detectors may reveal subtle deviations that signal the approach to the domain where the laws fail. The Penrose process and the ergosphere of rotating black holes add thermodynamic context. Energy can be extracted from a rotating black hole through the ergosphere. Up to roughly 29% of the mass energy is extractable for a maximally spinning black hole. The place where the laws fail is at the heart of the most efficient energy extraction engine in the cosmos. The concept of the scrambling time connects the failure to information dynamics. For Sagittarius A star, milliseconds. The information of anything crossing the horizon is scrambled at the maximum quantum rate, distributed across the black hole's 10 to the power of 77 microstates. The failure at the center is preceded by the fastest information processing in nature. But here is what makes this truly terrifying. The place where the laws no longer apply is hidden behind the event horizon. We cannot observe it, We cannot probe it. We cannot test our proposed replacements directly. The universe has placed the most important unsolved problem in physics behind an impenetrable barrier, visible only to those who fall through and forfeit the ability to report their findings. The observational constraints continue to accumulate. Each gravitational wave detection tests general relativity near the boundary of the place where the laws fail. Each Event Horizon Telescope observation constrains the near-horizon geometry. Future detectors, ground-based and space-based, will push sensitivity further. Each observation narrows the space of possible replacement laws. The tidal disruption events observed by optical and X-ray surveys confirm the tidal forces predicted by general relativity outside the singularity. Dozens have been observed. Thousands will be detected per year by the Vera Rubin Observatory. Each confirms the laws outside the singularity. Each constrains the possible form of the laws at the singularity. The measurement of tidal deformability through gravitational wave observations provides direct measurements of tidal interactions near event horizons. The love numbers of neutron stars, measured from the gravitational waveform, constrain the equation of state of dense matter and the physics of the regime approaching the failure. The thermodynamic constraints form the tightest web, the Bekenstein-Hawking entropy, the Hawking temperature, the four laws, the Page curve, all must be reproduced. The constraints are independent and complementary. Together they narrow the space of possible replacement laws dramatically. The Strominger-Vafa counting demonstrated that the entropy can be reproduced microscopically within string theory. The fuzzball program demonstrated that the microstates can be constructed explicitly. The holographic approach demonstrated that the entropy is the logarithm of the number of boundary states. Loop quantum gravity demonstrated that the entropy can be reproduced through the quantum geometry of the horizon. Each approach passes the entropy test. The convergence of independent approaches on the finiteness of the resolution is the strongest evidence. String theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety all agree. The place where the current laws fail is resolved at the Planck scale. The failure is finite, bounded, and followed by new physics. The place where the universe's laws no longer apply has motivated the most ambitious program in the history of theoretical physics. The search for laws that do apply everywhere, including at the singularity. Each major approach to quantum gravity offers a different set of replacement laws, a different picture of what happens at the place where the current laws fail. The first proposal is string theory. String theory replaces point particles with one-dimensional vibrating strings, roughly the Planck length in size. The strings have a minimum length. They cannot be compressed to zero size. The singularity, which requires compression to zero volume, cannot form. The place where the current laws fail is replaced by a stringy regime where the laws of string theory apply. The fuzzball program, developed by Samir Mathur, provides the most explicit string-theoretic picture. The entire classical interior, including the singularity, is replaced by a structure of strings and branes. The place where the laws failed in the classical theory is filled with quantum gravitational structure. The classical lawlessness is replaced by string-theoretic law. The number of fuzzball microstates matches the Bekenstein-Hawking entropy, 10 to the power of 77 for a solar mass black hole. The second proposal is loop quantum gravity. Spacetime is discrete at the Planck scale, composed of quanta of geometry connected by spin network edges. The singularity is replaced by a quantum bounce. When matter collapses to the Planck density, the discrete geometry generates a repulsive pressure that halts the collapse. The laws of loop quantum gravity apply at the Planck scale, replacing the infinite density with the Planck density. The Planck star, proposed by Carlo Rovelli and Francesca Vidotto, provides a concrete picture. The singularity is replaced by a compact object at the Planck density. The laws of loop quantum gravity govern this object. The classical lawlessness is replaced by quantum gravitational law. The place where the old laws failed becomes a place where new laws succeed. The Heisenberg uncertainty principle provides the most direct quantum argument against the place where the laws fail. At the singularity, matter is compressed to zero volume. Position is known exactly. But the uncertainty principle demands infinite uncertainty in momentum, infinite kinetic energy, infinite quantum pressure. The quantum laws forbid the singularity. The place where the classical laws fail is the place where the quantum laws demand something different. The non-renormalizability of general relativity is the technical expression of the failure. When physicists try to quantize gravity perturbatively, each order introduces new divergences. The number of free parameters grows without bound. The theory loses predictive power. The perturbative framework that works for the other forces fails for gravity. The place where the perturbative laws fail is where a non-perturbative framework is needed. The concept of the Planck scale provides the natural boundary between the old laws and the new laws. The for Planck length, roughly 10 to the power of negative 35 meters. The Planck time, roughly 10 to the power of negative 43 seconds. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. Below these scales, the classical laws work. Above them, the classical laws fail. The Planck scale is the frontier. The connection between the failure and the concept of the four laws of black hole mechanics provides thermodynamic constraints. The zeroth law says surface gravity is constant. The first law relates mass, area, angular momentum, and charge. The second law says area never decreases. The third law says surface gravity cannot be reduced to zero. These thermodynamic properties of the exterior constrain the failure at the interior. Any replacement laws must reproduce these thermodynamic relationships. The exterior thermodynamics is finite and well-defined. The interior must be compatible. The infinite failure is thermodynamically incompatible with the finite exterior. The gap between the Planck scale and our experimental capabilities is roughly 17 orders of magnitude. The smallest distances probed by the Large Hadron Collider are roughly 10 to the power of negative 18 meters. The Planck length is roughly 10 to the power of negative 35 meters. No foreseeable technology can bridge this gap directly. The laws that apply at the place where the current laws fail must be discovered through mathematical reasoning and consistency arguments. The connection between the failure and the concept of the holographic principle is fundamental. The Bekenstein-Hawking entropy scales with area, not volume. The three-dimensional interior is encoded on the two-dimensional boundary. The failure of the three-dimensional laws at the singularity is a failure of the projected description, not of the fundamental one. The fundamental two-dimensional laws never fail. The Ryuta-Kakanagi formula connects entanglement on the boundary to geometry in the bulk. The quantum version leads to the island formula. These formulas establish the mathematical connection between the laws that work, boundary quantum mechanics, and the laws that fail, bulk geometry. The connection between working laws and failing laws is itself governed by a law, the holographic map. The ER equals EPR conjecture, proposed by Susskind and Maldacena in 2013, suggests that entanglement and wormholes are the same phenomenon. The place where the geometric laws fail may be a hub of quantum connectivity, connected to the exterior through microscopic wormholes generated by entanglement. The failure of the geometric laws does not mean disconnection. It means connection through a different framework. The concept of the Penrose process connects the failure to energy dynamics. Energy can be extracted from the ergosphere of a rotating black hole. Up to roughly 29% of the mass energy is extractable for a maximally rotating black hole. The place where the laws fail is at the heart of the most efficient energy extraction engine in the cosmos. The connection between all the proposals and the concept of the Penrose-Hawking singularity theorems is important. The theorems guarantee the singularity within classical general relativity. They require positive energy density and the existence of trapped surfaces. Every quantum gravity proposal avoids the singularity by modifying these assumptions. Loop quantum gravity violates the energy condition through quantum corrections. String theory modifies the geometry through the finite size of strings. The holographic principle replaces the bulk description with a boundary description that has no singularity. Each proposal evades the theorems by changing the mathematical framework on which they rest. The concept of geodesic incompleteness illustrates the nature of the classical failure. Geodesics terminate at the singularity. The world lines of freely falling particles end. The mathematical description has a boundary. The quantum resolution replaces this termination with continuation. A bounce-in-loop quantum gravity, a fuzzball interaction in string theory, smooth boundary evolution in holographic duality. The geodesics continue in some form through the Planck scale transition. The concept of the Planck star provides the most concrete physical picture of the replacement. The singularity is replaced by a compact object at the Planck density. The laws of loop quantum gravity govern this object. The tidal forces reach the Planck curvature and halt. The geometric laws of general relativity are replaced by the discrete laws of quantum geometry at this scale. The concept of observer complementarity connects the failure to the perspective of the observer. The outside observer sees no failure. Information is processed on the stretched horizon and returned as Hawking radiation. The laws of the boundary description apply without interruption. The falling observer sees the interior and the approach to the failure. Both descriptions are valid. The failure is observer-dependent. This observer dependence challenges the assumption that there is a single objective description of the place where the laws fail. The failure looks different from different perspectives. From the boundary perspective, no failure occurs. From the bulk perspective, the failure is dramatic. The truth depends on who is asking and from where. The concept of the black to white hole transition connects the failure to a future. The collapsed matter bounces at the Planck core. The place where the old laws failed becomes a passage to a white hole. The failure is temporary. The new laws govern the transition. The laws never truly fail. They transform. The concept of the Bekenstein bound connects the failure to the limits of information. Black holes saturate the Bekenstein bound. They contain the maximum information for their mass. The place where the laws fail is the place of maximum information density. The failure of the geometric laws is the failure of geometry to represent the maximum informational complexity. Connects the concept of the quantum bounce, connects the failure to a specific physical process. The collapse halts at the Planck density. The matter bounces. The contraction becomes expansion. The laws that govern the bounce are the laws of quantum geometry, finite and well-defined. The place where the old laws failed becomes the place where the new laws produce their most dramatic prediction, the reversal of collapse. The thermodynamic constraints provide independent verification. The Bekenstein-Hawking entropy, the Hawking temperature, the four laws, the Page curve, all must be reproduced by any replacement laws. The constraints form a tight web. The surviving proposals satisfy them. The new laws are tightly constrained and well tested against the thermodynamics. The third proposal comes from the holographic principle and ADS-CFT. Juan Maldasena's 1997 discovery showed that a theory of gravity in anti-de Sitter space is equivalent to a quantum field theory on the boundary. The boundary theory is well-defined, unitary, and singularity-free. The laws of the boundary theory apply everywhere, including at the point that corresponds to the singularity in the bulk. The numbers are striking. The boundary theory has no singularity. The laws of the boundary theory never fail. The place where the bulk laws fail corresponds to something smooth and finite in the boundary description. The classical lawlessness in the bulk is an artifact of the bulk description, not a feature of the fundamental physics. The fourth proposal involves quantum error correction and emergent spacetime. The bulk geometry is encoded in the boundary through a quantum error correcting code. Away from the singularity, the code is robust and the geometric laws apply. Near the singularity, the code degrades. At the singularity, it fails. The place where the geometric laws no longer apply is the place where the error-correcting code has broken down, but the boundary laws still apply. The quantum state on the boundary evolves smoothly and unitarily. The failure is in the translation from boundary to bulk, in the holographic map that generates the geometric description. The laws fail in the derived description, but not in the fundamental one. The fifth proposal is the island formula and replica wormholes. The gravitational path integral, when properly computed with replica wormhole contributions, produces finite, unitary answers. The singularity, present in individual classical geometries, is washed out in the quantum sum. The laws of the full quantum gravitational path integral apply everywhere. The classical singularity is an artifact of restricting to a single classical geometry. The sixth proposal is causal set theory. Spacetime is fundamentally discrete, composed of atoms of spacetime connected by causal relations. In a discrete spacetime, the point-like singularity cannot form. The laws of causal set theory apply at all scales. The place where the continuum laws fail is replaced by a discrete structure where discrete laws apply. The seventh proposal is asymptotically safe gravity. The gravitational coupling approaches a finite fixed point at high energies. The laws remain well defined at all scales. The infinite quantities become finite. The place where the perturbative laws fail is the place where the non-perturbative fixed point laws take over. The convergence of all approaches on the finiteness of the resolution at the Planck scale is powerful evidence. When independent mathematical frameworks, starting from different assumptions and using different techniques, arrive at the same conclusion, the probability that the conclusion is wrong decreases significantly. The place where the current laws fail is almost certainly resolved by quantum gravitational effects at the Planck scale. The thermodynamic constraints reinforce this convergence. The Bekenstein-Hawking entropy, the Hawking temperature, the four laws of black hole mechanics, the Page curve, all must be reproduced by any replacement laws. The constraints are independent and complementary. Together they form a tight web that narrows the space of possible new laws to a small family, all sharing the key property: finiteness at the Planck scale. The practical applications continue to emerge. Quantum error correction, tensor networks, holographic methods, scrambling dynamics, each was driven by the study of the place where the laws fail. Each has found applications far beyond black hole physics. The most inaccessible place in the universe has generated some of the most useful tools in modern science. The eighth proposal involves computational complexity. Susskind proposed that the interior volume grows with quantum complexity. The place where the laws no longer apply is the place where the complexity exceeds the descriptive capacity of geometry. The geometric laws fail because the quantum state has become too complex for any geometric description. The fundamental laws, expressed in the language of quantum information, continue to apply. The concept of the scrambling time provides the temporal scale for information processing at the place where the laws fail. For Sagittarius A star, the scrambling time is milliseconds. The Margulis-Levitin theorem sets the maximum speed of quantum evolution. Black holes saturate this bound. The place where the old laws fail is also the place of maximum quantum activity, operating at the absolute physical limit. The Hayden-Preskel protocol shows that individual quantum bits can be recovered from the Hawking radiation after one scrambling time. The information that enters the place where the laws fail is not permanently lost. It is scrambled, distributed, and eventually returned. The failure of the laws does not mean the failure of information. Information survives where geometry does not. The connection between the proposals and the observational constraints is growing. Each gravitational wave detection tests general relativity. Each event horizon telescope observation constrains the near-horizon geometry. Future detectors will push further. LISA will detect supermassive mergers. The Einstein telescope and Cosmic Explorer will increase ground-based sensitivity. The photon ring may be resolved. Each observation narrows the space of possible replacement laws. The tidal disruption events observed by optical and X-ray surveys confirm the tidal force predictions of general relativity outside the singularity. Each event a test of the laws in the regime of extreme tidal forces. The upcoming Vera Rubin Observatory will detect thousands per year. Each detection constrains the physics at distances above the Planck scale. The practical applications of the tools developed to study the failure continue to grow. Quantum error correction for quantum computing, holographic methods for material science, scrambling dynamics for quantum simulation, tensor networks for machine learning. The place where the laws fail has generated tools that work everywhere else. The study of the place where the laws fail has revealed unexpected connections across disciplines. The holographic principle connected gravity to quantum information theory. The ADS-CFT correspondence connected string theory to condensed matter physics. Quantum error correction connected black holes to quantum computing. The firewall paradox connected quantum foundations to general relativity. Penrose's singularity theorems introduced topological methods to general relativity. Each connection was driven by the study of the failure. The place where the laws fail has been one of the most productive catalysts for scientific advance. The practical applications continue to expand. Quantum error correction for fault-tolerant quantum computing, tensor networks for machine learning, holographic methods for strongly coupled quantum materials, scrambling dynamics for quantum simulation, random quantum circuits for benchmarking quantum processors. Each application was driven, directly or indirectly, by the study of the failure. The next generation of observations will tighten the constraints. The Einstein telescope and cosmic explorer will increase gravitational wave sensitivity. LISA will detect supermassive mergers. The Event Horizon telescope will sharpen its images. The photon ring may be resolved. The convergence of theory and observation is narrowing the space of possible new laws. The connection between the failure and the concept of the multiverse is speculative. The Kerr mathematics permits paths through the ring singularity into different spacetimes. If the quantum resolution preserves this feature, the place where the laws fail might be a passage between universes. This remains far from established physics. The connection between the failure and the concept of the initial cosmological singularity is important. Many cosmological models predict a singularity at the beginning. If the black hole singularity is resolved by quantum gravity, the cosmological singularity may be resolved by the same mechanism. Loop quantum cosmology replaces the initial singularity with a quantum bounce. The same laws that resolve the place where the laws fail inside black holes may resolve the place where the laws fail at the beginning of cosmic history. The Page curve describes the informational life cycle of the black hole. Rising entropy during the first half of evaporation, falling entropy during the second half. The island formula reproduces this curve. The information is preserved through the failure. The laws that govern information preservation are not the laws that fail. The laws that fail are the laws of geometry. The laws that survive are the laws of quantum information. The concept of black hole complementarity provides another perspective. The outside observer sees information processed on the stretched horizon. The falling observer sees the interior and the approach to the singularity. Both descriptions are valid. The place where the laws fail looks different depending on who is asking. The failure is observer-dependent. The laws that fail and the laws that apply depend on the observer's perspective. The thermodynamic constraints from the Bekenstein-Hawking entropy, the Hawking temperature, and the four laws of black hole mechanics form a tight web. Any replacement laws must reproduce these properties. The new laws are constrained by the old thermodynamics. The place where the laws fail has finite, well-defined thermodynamic properties that the new laws must match. The Weyl curvature hypothesis, proposed by Roger Penrose, connects the failure to the arrow of time. The initial cosmological singularity has low Weyl curvature and low entropy. The black hole singularity has high Weyl curvature and high entropy. The place where the laws fail has a thermodynamic orientation. It is the endpoint of entropy production, the thermodynamic destination of the universe. The convergence across all these proposals is the most important result. Every approach agrees that the place where the current laws fail is the place where new laws must apply. Every approach identifies the Planck scale as the transition point. Every approach replaces the classical infinity with something finite. The current laws fail, but laws do not fail. Different laws take over. The connection between all the proposals and the concept of the arrow of time provides cosmological perspective. The place where the laws fail is the thermodynamic endpoint. The arrow of time points toward it. The entropy increases during the fall. The black hole is the maximum entropy object. The failure is at the endpoint of entropy production. The new laws must describe this maximum entropy state consistently with the second law of thermodynamics. The connection between the proposals and the concept of black hole complementarity means the failure looks different from different perspectives. The outside observer sees more failure. Information is processed on the stretched horizon and returned as Hawking radiation. The falling observer sees the interior and the approach to the failure. Both descriptions are valid. The failure is observer-dependent. The math is striking. The Planck density is roughly 5.1 times 10 to the power of 96 kilograms per cubic meter. The Planck length is roughly 10 to the power of negative 35 meters. Every approach identifies these as the frontier between the old laws and the new laws. Below the Planck density, general relativity works. Above it, quantum gravity takes over. The place where the old laws no longer apply is the place where the new laws begin. The connection between the proposals and the concept of the initial cosmological singularity is important. Many cosmological models predict a singularity at the beginning of cosmic history. If the black hole singularity is resolved by quantum gravity, the cosmological singularity may be resolved by the same mechanism. Loop quantum cosmology replaces the initial singularity with a quantum bounce. The same laws that apply at the place where the current laws fail inside black holes may apply at the earliest moments of cosmic history. The concept of the Planck density as the natural cutoff connects all the proposals. Every approach identifies the Planck density as the boundary between the domain of the old laws and the domain of the new laws. Below the Planck density, general relativity applies. Above it, quantum gravity applies. Planck density is the frontier between the known and the unknown, between the laws that work and the laws that are being discovered. The concept of the holographic principle as the fundamental framework provides the broadest perspective. The three-dimensional failure is a feature of the projected description. The two-dimensional fundamental description has no failure. The laws of the boundary theory apply everywhere. The place where the bulk laws fail is smooth and well-defined on the boundary. The failure is in the projection, not in reality. The concept of the Bekenstein-Hawking entropy as a constraint on the new laws deserves final emphasis. The entropy of a solar mass black hole is roughly 10 to the power of 77. Any proposal that replaces the failure must accommodate this number. The fuzzball program does so through explicit microstate counting. The holographic approach does so through boundary states. Loop quantum gravity does so through the quantum geometry of the horizon. Each passes the entropy test. The entropy is the tightest quantitative constraint on the new laws. The Hawking temperature, inversely proportional to mass, provides the thermal dimension. For a solar mass black hole, roughly 60 billionths of a Kelvin, the new laws must be consistent with this temperature. The evaporation time, roughly 10 to the power of 67 years, sets the timescale for the return of information. The new laws must describe the evaporation process consistently, and this is where the answer becomes deeply unsettling, because the convergence tells us that the laws do not truly fail at the singularity. Different laws apply. The place where the universe's laws no longer apply is not a place of lawlessness. It is a place where the current laws give way to deeper, more fundamental laws that we have not yet fully discovered. The deeper truth about the place where the universe's laws no longer apply is that it is not a place of lawlessness at all. It is a place where one set of laws gives way to another. The failure of general relativity at the singularity is not the failure of all laws. It is the failure of one particular set of laws, the laws of smooth, continuous, classical spacetime. At the singularity, these laws are replaced by deeper laws, the laws of quantum gravity, which are more fundamental, more general, and more precisely attuned to the nature of reality at the Planck scale. The history of physics is a history of such transitions. Classical mechanics was not the final law. It was replaced by quantum mechanics at the atomic scale. Newtonian gravity was not the final law. It was replaced by general relativity at the extreme of mass and velocity. In each case, the old law failed at a specific boundary, and the new law took over, reducing to the old law in the appropriate limit. The place where the universe's laws no longer apply is the latest boundary. The laws of general relativity, which have served physics so brilliantly for more than a century, reach their limit at the Planck scale. New laws, the laws of quantum gravity, take over. The place where the old laws fail is the birthplace of the new laws. The connection between the failure and the concept of consciousness is speculative but unavoidable. A conscious observer falling into a supermassive black hole would experience the interior firsthand. They would observe the laws working, describing every tidal force and visual distortion, right up to the moment of failure. Whether consciousness persists through the Planck scale transition is unknown. Whether the concept of experience has meaning at the place where the geometric laws fail is a question beyond current physics. The concept of the scrambling time connects the failure to the temporal experience. For Sagittarius A star, the scrambling time is milliseconds. The information of the falling observer is scrambled almost immediately after crossing the horizon. The physical body falls for 20 seconds. The information identity is scrambled in thousandths of a second. The failure of the laws at the center occurs after both the physical body and the informational identity have been processed by the extreme environment. The concept of the Planck scale as the boundary between the old laws and the new provides the ultimate framework. Below the Planck density, the old laws work. Above it, the new laws apply. The boundary is sharp. The transition is determined by the three fundamental constants: Newton's gravitational constant, the speed of light, and Planck's reduced constant. These constants define the natural scales at which the old laws end and the new laws begin. The resolution of the failure will be the most important scientific achievement since the development of quantum mechanics. It will provide the laws that apply everywhere, including the Planck scale, including the center of every black hole. It will unify gravity with quantum mechanics. It will resolve the singularity. It will preserve information. It will describe the emergence of spacetime from quantum information, and it will transform our understanding of reality at the deepest level. Let that sink in. The holographic principle provides the most concrete evidence for the existence of the new laws. If the three-dimensional bulk spacetime is a projection of two-dimensional boundary physics, then the laws of the boundary theory are the fundamental laws. They apply everywhere, including at the singularity. The place where the bulk laws fail corresponds to a smooth, well-defined region in the boundary description. The fundamental laws never fail. Only the derived, projected, geometric laws fail. Mark van Ramsdonk showed in 2010 that entanglement generates spacetime. The laws that generate spacetime from entanglement are more fundamental than the laws of the generated spacetime. At the singularity, where the generated spacetime breaks down, the generating laws continue to operate. The place where the universe's geometric laws no longer apply is the place where the universe's informational laws are most visible. The connection between all these proposals and the emergence of spacetime provides the unifying theme. Every proposal suggests that the smooth, continuous spacetime of general relativity is an approximation that breaks down at the Planck scale. The place where the laws fail is the place where the approximation breaks. The failure is not in the laws. It is in the approximation on which the laws are built. If spacetime is emergent, arising from quantum information and entanglement, then the laws of spacetime geometry are derived laws, secondary to the more fundamental laws of quantum information. The failure of the derived laws at the singularity does not imply the failure of the fundamental laws. The fundamental laws continue to operate. The derived laws which produce the geometric description of space-time lose coherence at the singularity. Mark van Ramsdonk showed that entanglement generates space-time. Near the singularity, the entanglement structure is maximally disrupted. The emergent spacetime is maximally distorted. The geometric laws fail, but the entanglement laws, the informational laws, the fundamental laws continue to operate. The place where the geometric laws no longer apply is the place where the informational laws are most visible. The error-correcting code of holographic spacetime provides the mechanism. The bulk geometry is encoded redundantly in the boundary. Away from the singularity, the code is robust and the geometric laws apply. Near the singularity, the code degrades. At the singularity, the code fails and the geometric laws break down. But the boundary laws, the laws of the encoding, continue to function perfectly. The concept of the Planck star provides the most concrete physical picture of what replaces the place where the laws fail. The singularity is replaced by a compact object at the Planck density. The laws of loop quantum gravity govern this object. The tidal forces halt at the Planck curvature. The geometric laws of general relativity are replaced by the discrete laws of quantum geometry. The place where the old laws failed can place where new laws succeed. The black to white hole transition connects the failure to a future where the laws succeed again. The collapsed matter bounces at the Planck core and re-emerges. The information survives. The place of failure is a passage, not a terminus. The laws that apply during the bounce govern the transition from collapse to expansion. The concept of the arrow of time adds cosmological weight. The place where the laws fail is the thermodynamic endpoint. The arrow points toward it. The entropy increases. The black hole is the maximum entropy object. The failure is the endpoint of entropy production. The new laws must describe this maximum entropy state. The connection between the failure and the nature of consciousness is speculative, but worth noting. Consciousness depends on information processing. At the place where the laws fail, information processing is disrupted. Whether consciousness can persist through the failure is unknown. The question connects physics to philosophy. The resolution will be the most important scientific achievement since quantum mechanics. It will provide the laws that apply everywhere. It will resolve the singularity. It will unify gravity and quantum mechanics, and it will reveal the nature of space-time at the most fundamental level. The gravitational path integral, summing over all space-time geometries including replica wormholes, produces finite unitary answers. The singularity is washed out in the quantum sum. Individual classical geometries contain the place where the laws fail. The quantum sum does not. The full quantum theory has no place where the laws fail. The failure is an artifact of the classical approximation. The computational complexity perspective adds dynamics. The interior grows because quantum complexity increases. The geometric laws describe this growth. At the singularity, the complexity exceeds the geometric capacity. The geometric laws fail, but the computational laws continue. The place where the geometric laws fail is the point where computation exceeds representation. The convergence of independent approaches is the strongest theoretical evidence. String theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, the gravitational path integral, all agree. The place where the current laws fail is the place where deeper laws apply. The failure is not lawlessness. It is the transition between laws. The error-correcting structure of holographic spacetime, discovered by Daniel Harlow and collaborators, provides the mechanism. The bulk geometry is encoded in the boundary through a quantum error-correcting code. The geometric laws are the laws of the encoded description. At the singularity, the encoding breaks down. The geometric laws fail, but the boundary laws, the laws of the encoding, continue to function. The place where the encoded laws fail is the place where the encoding laws are exposed. The tools developed for the study of the failure have practical importance far beyond astrophysics. Quantum error correction for quantum computing was inspired by the holographic structure of space-time. Tensor networks for machine learning were inspired by the structure of holographic space-time. Scrambling dynamics for quantum simulation were inspired by black hole information processing. The most abstract problem in physics has generated some of the most practical tools in modern science. The philosophical implications are profound. If the laws fail at the singularity, our current understanding is incomplete. The laws we have are not final. Deeper laws exist. The failure is the proof. The singularity is the evidence. The place where the laws no longer apply is the most compelling argument for the existence of more fundamental laws. The connection between the failure and the nature of mathematics deserves final reflection. If mathematics is the language of nature, and if mathematical language fails at the singularity, then we are using the wrong mathematical language. The correct mathematical language, the language of quantum gravity, will describe the singularity without producing infinity. The failure of the current mathematical language is not a failure of mathematics. It is a signal that a better mathematical language is needed. The next generation of physicists will find that language. They will have quantum computers. They will have improved detectors. They will have refined theoretical frameworks. The place where the laws fail will become the place where the deepest laws are discovered. and the discovery will be the most profound achievement in the history of science. This is not science fiction. These are rigorous mathematical results within the ADS-CFT framework, confirmed by multiple independent calculations, constrained by the information paradox, the firewall, and the thermodynamics of black holes. The Wheeler-DeWitt equation, one of the earliest attempts at quantum gravity, has no time variable. If the fundamental laws have no time, then time is emergent. The laws of spacetime, which treat time as fundamental, are derived from more fundamental laws that do not include time. At the singularity, where time ends in the classical description, the timeless fundamental laws continue to operate. The place where the time-dependent laws fail is the place where the timeless laws are most relevant. The computational complexity perspective adds dynamical content. Susskind proposed that the interior volume grows with quantum complexity. The geometric laws describe this growth as long as the complexity is within the geometric capacity. At the singularity, the complexity exceeds the capacity. The geometric laws fail, but the computational laws continue. The place where the geometric laws no longer apply is the place where the computational laws take over. The Bekenstein-Hawking entropy provides quantitative confirmation. The entropy of a solar mass black hole is roughly 10 to the power of 77. This number tells us the information content of the place where the laws fail. The new laws must accommodate this information. The fuzzball program accommodates it through explicit microstate counting. The holographic approach accommodates it through boundary states. Loop quantum gravity accommodates it through quantum geometry. Each approach produces the correct entropy, confirming that the new laws are consistent with the thermodynamics. The concept of the page time adds temporal structure. The page time is the half point of evaporation. Before it, the entropy of the Hawking radiation rises. After it, the entropy falls. The information begins to emerge. The failure has an informational expiration date. The scrambled information is returned on the evaporation timescale, roughly 10 to the power of 67 years for a solar mass black hole. The concept of quantum complexity provides the dynamical perspective. The interior grows because quantum complexity increases. At the singularity, complexity exceeds geometric capacity. The geometric laws fail. The computational laws continue. The failure is a capacity limit of the geometric language, not a failure of all languages. The scrambling time for Sagittarius A star is milliseconds. The new laws must describe information processing at this speed. The Margulis-Levitin theorem sets the maximum. Black holes saturate it. The place where the old laws fail is also the place of maximum quantum activity. The new laws govern the fastest information processing in nature. The page curve, the mathematical signature of unitary evolution during evaporation, has been reproduced by the island formula. The new laws must produce this curve. They do. The information is preserved. The new laws, whatever their precise form, are consistent with unitarity. The place where the old laws fail is a place where the new laws preserve information. The concept of the Ryu-Takayanagi formula connects the failure to the mathematical bridge between quantum information and geometry. The entanglement entropy on the boundary equals the area of the minimal bulk surface. The quantum version leads to the island formula. These formulas establish the precise mathematical connection between the laws that work, boundary quantum mechanics, and the laws that fail, bulk geometry. The failure of the geometric laws is encoded in the entanglement structure through these formulas. The concept of the replica wormholes ensures unitarity through the gravitational path integral. Without replica wormholes, information appears to be lost. With them, information is preserved. The new laws include these exotic contributions. The place where the old laws fail is the place where the new laws produce their most important prediction. The preservation of information through the page curve. The concept of quantum error correction shows how information survives the failure. The boundary state is encoded redundantly. The code protects the information even when the geometric projection fails. The new laws include the error-correcting structure. The place where the old laws fail is the place where the error-correcting structure is most visible and most essential. The deeper truth is that the place where the universe's laws no longer apply is not a place of anarchy, it is a place of transition, a frontier between the laws we know and the laws we are discovering, a boundary between the old physics and the new physics, a threshold that separates the domain of general relativity from the domain of quantum gravity. What does it mean that the universe contains a place where its current laws fail? What does this tell us about the nature of physical law, about our understanding of reality, about the relationship between mathematics and the physical world? The observational constraints from gravitational wave astronomy continue to tighten. Each detection tests general relativity in the strong field regime. The ring-down signals test the no-hair theorem. Future detectors, including LISA, the Einstein telescope, and Cosmic Explorer, will push sensitivity further. The photon ring may be resolved by the Event Horizon telescope. Each observation constrains the laws that apply at the region just outside the place where the current laws fail. The tidal disruption of stars by supermassive black holes provides direct observational evidence for the extreme tidal forces predicted by the laws. Dozens of events have been observed. The upcoming Vera Rubins Observatory will detect thousands per year. Each detection confirms the laws outside the singularity and constrains the possible form of the laws at the singularity. The gravitational wave signature of neutron star black hole mergers provides information about tidal interactions near the event horizon. The tidal deformability of neutron stars, measured through gravitational waveforms, constrains the equation of state of dense matter. Future detections may measure whether neutron stars are disrupted outside the horizon, testing the Roche limit physics near the boundary of the place where the laws fail. The connection between the failure and the concept of the Planck star provides a specific physical picture. The singularity is replaced by a compact object at the Planck density. The laws of loop quantum gravity apply at the Planck star. The geometric laws of general relativity give way to the discrete laws of quantum geometry. The place where the old laws fail becomes a place where new discrete laws succeed. The concept of the quantum bounce connects the failure to a specific physical process. When matter collapses to the Planck density, the discrete quantum geometry generates a repulsive pressure. The collapse halts, the matter bounces. The place where the old laws predicted infinite density is replaced by a place where new laws produce finite, maximum density. The failure is resolved by the bounce. The black-to-white hole transition, explored by Haggard and Rovelli, connects the place where the laws fail to a future where the laws succeed again. The collapsed matter bounces and re-emerges. The place of failure is a passage, not a terminus. The laws that apply during the bounce govern the transition from collapse to expansion. The thermodynamic constraints must be satisfied by any new laws. The Bekenstein-Hawking entropy, the Hawking temperature, the four laws of black hole mechanics, the Page curve, all must be reproduced. The constraints are severe. The surviving proposals all satisfy them. The new laws are tightly constrained by the old thermodynamics. It means, first, that our current laws are not the final laws. General relativity, despite its extraordinary precision and its century of confirmation, is not the ultimate description of gravity. It is an approximation, valid at curvatures below the Planck scale, that breaks down at the most extreme conditions. The failure at the singularity is the proof of incompleteness, written into the equations themselves. There is a philosophical pause required here. The existence of a place where the laws fail challenges one of the deepest assumptions of science, that the laws of nature are universal. If the laws fail at the singularity, are they truly universal? The answer, emerging from the theoretical landscape, is that the current laws are not universal. They are effective laws, valid in a specific domain. The truly universal laws, the laws of quantum gravity, are deeper, more fundamental, and not yet fully known. The failure at the singularity is the proof that deeper laws exist. Every previous failure of physical law, the failure of classical mechanics at the speed of light, the failure of Newtonian gravity at extreme masses, the failure of classical electromagnetism at the atomic scale, has been followed by the discovery of deeper laws that resolved the failure. The pattern is clear. The failure at the singularity will be followed by the discovery of the laws of quantum gravity. the philosophical dimension of the failure deserves final reflection. The existence of a place where the laws fail challenges the assumption of universality. But the resolution, emerging from the convergence of independent approaches, suggests that universality is preserved at a deeper level. The current laws are not universal. The deeper laws of quantum gravity are. The place where the current laws fail is the frontier where the deeper laws begin. The concept of emergence provides the unifying framework. Spacetime is emergent. The laws of spacetime geometry are emergent. The failure at the singularity is the failure of the emergent description. The fundamental laws from which spacetime emerges continue to operate. The failure is a failure of the derived description, not of the fundamental reality. The connection between the failure and the initial singularity of cosmological models adds cosmic scope. If the black hole singularity is resolved by quantum gravity, the cosmological singularity may be resolved by the same mechanism. The same laws that apply at the place where the current laws fail inside black holes may apply at the earliest moments of cosmic history. The resolution has implications far beyond black holes. The study of the place where the laws fail has generated advances across theoretical physics, mathematics, quantum information science, and observational astrophysics. Quantum error correction, holographic methods, scrambling dynamics, gravitational wave astronomy. Each was driven by the attempt to understand the failure. The failure has been one of the most productive catalysts for scientific advance in the history of science. The next generation of physicists will resolve the failure. They will discover the laws that apply everywhere, including the Planck scale, including the center of every black hole. The place where the laws no longer apply will become the place where the deepest laws were discovered, and the discovery will transform our understanding of the universe at its most fundamental level. The practical implications have been substantial. The study of the place where the laws fail has driven the development of the holographic principle, the AD-SCFT correspondence, quantum error correction, the island formula, and the connection between entanglement and geometry. Each represents a major advance. Each was motivated by the need to find laws that work where the current laws fail. The observational landscape continues to evolve. Roughly 90 gravitational wave events have been detected. The Event Horizon Telescope has photographed 2 supermassive black hole shadows. Future detectors will push sensitivity further. Each observation tests the exterior predictions of general relativity. Each constrains the possible form of the new laws that apply at the singularity. The mathematical tools developed for this problem have applications across science: quantum error correction for quantum computing, holographic methods for condensed matter physics, scrambling dynamics for quantum simulation, tensor networks for machine learning. The place where the laws fail has generated tools that work everywhere. The connection between the failure and the nature of spacetime provides the deepest implication. If the laws of geometry fail at the singularity, and if spacetime is emergent, then the failure is a failure of the emergent description, not of reality. The fundamental laws, expressed in the language of quantum information, continue to apply. The failure of the geometric laws reveals the informational laws that underlie them. The next generation of physicists will discover the new laws. They will have quantum computers capable of simulating aspects of quantum gravity. They will have gravitational wave detectors of unprecedented sensitivity. They will have theoretical frameworks more refined than anything available today. The place where the laws no longer apply will become a place where new laws are confirmed. Let that sink in. The connection between the failure and the nature of reality provides the deepest perspective. If the laws that fail are the laws of smooth, continuous spacetime, and if spacetime is emergent, then the failure reveals the non-geometric quantum substrate from which spacetime emerges. The place where the laws fail is a window into the deepest structure of reality. Through the failure, the quantum informational foundation of the universe is visible. The failure forces the deepest questions in physics to become unavoidable. What is spacetime made of? Is information more fundamental than geometry? Is time emergent? What does it mean for something to exist at the Planck scale? These questions, which philosophers have debated for millennia, become precise scientific questions at the place where the laws fail. The answers will come from quantum gravity. The resolution will have implications far beyond black holes. It will provide the mathematical language for the early universe, for extreme gravitational environments, for the quantum structure of space-time at all scales. It will connect gravity to the other forces. It will unify the description of nature at the most fundamental level. The place where the universe's laws no longer apply is temporary. It will be filled, eventually, with laws that do apply. The failure will become a success. The lawlessness will become law. The most important unsolved problem in physics will become the most important solved problem in physics. The place where the laws produced infinity will become the place where deeper laws produce finite, meaningful, physically interpretable answers. The place of lawlessness will become the place of the deepest law. The singularity, which has haunted theoretical physics for more than a century, will be resolved. The infinity will be replaced by the Planck density. The termination of geodesics will be replaced by the quantum bounce. The failure of the mathematical description will be replaced by the success of a deeper mathematical description. The place where the universe's laws no longer apply will become the place where the universe's deepest laws were first understood. And the understanding will transform every field of physics, from cosmology to particle physics to quantum information, revealing the mathematical structure of reality at its most fundamental level. The connection between the failure and the concept of information as a physical quantity is one of the deepest threads. Information, in the physicist's sense, is the complete specification of the quantum state. The laws of quantum mechanics say information is always preserved. The failure at the singularity threatens to violate this preservation. The new laws must preserve information. The island formula shows that they do. The page curve is reproduced. Information survives where geometry does not. The Bekenstein-Hawking entropy formula, S equals A over 4 in Planck units, is the Rosetta Stone connecting the failing laws to the succeeding ones. The formula connects gravity through the area, thermodynamics through the entropy, and quantum mechanics through the Planck units. Any new laws must reproduce this formula. Every successful proposal does. The formula is the bridge between the old laws and the new laws. The concept of the arrow of time connects the failure to thermodynamics. Black holes are maximum entropy objects. The total entropy of all black holes dominates the cosmic entropy budget. The place where the laws fail is the thermodynamic endpoint. The arrow of time points toward it. The new laws must be consistent with this arrow. They must describe the maximum entropy state. The scrambling time provides the temporal scale for information processing at the place where the laws fail. For Sagittarius A star, milliseconds. The Margulis-Levitin theorem sets the maximum speed. Black holes saturate it. The new laws must describe processing at this speed. The Hayden-Preskill protocol shows that information can be recovered after one scrambling time. The new laws must be consistent with this recovery. The concept of the Bekenstein bound sets the maximum information content. Black holes saturate it. The place where the laws fail contains the maximum possible information for its mass. The new laws must describe this maximum density of information. The failure of the geometric laws at this point is the failure of geometry to represent the maximum informational complexity. The place where the universe's laws no longer apply is at the center of every black hole. It is the singularity, the point where the curvature of space-time diverges, the density becomes infinite, the tidal forces become unbounded, and the mathematical description of reality produces results that have no physical meaning. The laws that fail are the laws of general relativity, the most precisely tested theory in the history of physics. They describe the orbits of planets, the bending of starlight, the emission of gravitational waves, the expansion of the cosmos with extraordinary accuracy, and then, at one point, at the center of every black hole, they produce infinity. The most successful laws in the history of science fail at the most extreme conditions the universe can produce. But the failure is not the end of the story, it is the beginning. Every previous failure of physical law has been followed by the discovery of deeper, more fundamental laws. The failure of Newtonian mechanics led to special relativity, and quantum mechanics. The failure of classical electromagnetism led to quantum electrodynamics. The failure of the Fermi theory led to the electroweak theory. Each failure was a signpost, pointing toward deeper physics. The failure at the singularity is the latest and deepest signpost. It points toward quantum gravity, a set of laws that apply everywhere, including at the Planck scale, including at the center of every black hole. The laws of quantum gravity will resolve the singularity, replace the infinity with something finite, preserve information, and describe the nature of spacetime at the most fundamental level. The proposals are many: string theory and fuzzballs, loop quantum gravity and Planck stars, holographic duality and boundary quantum mechanics, quantum error correction, the island formula, causal set theory, asymptotic safety. Each captures a piece of the truth. The convergence across all approaches provides confidence. The singularity is not real. The laws do not truly fail. Deeper laws apply. The place where the universe's laws no longer apply is the universe's most important unsolved problem. It is the most direct evidence that our understanding is incomplete. It is the most powerful motivation for the search for quantum gravity. And it is the most closely guarded secret in nature, hidden behind the event horizons of billions of black holes, sealed away from direct observation, accessible only to those who fall through and forfeit the ability to report their discoveries. The Wheeler-DeWitt equation, one of the earliest formulations of quantum gravity, has no time variable. The quantum state of the universe is static. Time is emergent. The place where time ends in the classical description, at the singularity, is the place where the emergence of time fails. The timeless fundamental laws continue to operate. The time-dependent derived laws fail. The problem of time in quantum gravity is directly connected to the failure at the singularity. In quantum gravity, there is no background time. Time must be reconstructed from the quantum state. At the singularity, where classical time ends, the reconstruction fails. But the fundamental state persists. The failure of time is a failure of the derived quantity, not of the fundamental state. The concept of the Planck scale marks the boundary between the domains of the old and new laws. The Planck length, the Planck time, the Planck density are the natural scales of quantum gravity. At these scales, both general relativity and quantum field theory reach their limits. The new laws of quantum gravity begin at these scales. The place where the old laws fail is the birthplace of the new laws. The concept of the holographic principle provides the most radical reinterpretation of the failure. If the three-dimensional interior is a projection of two-dimensional boundary physics, then the place where the three-dimensional laws fail is not a failure of reality. It is a failure of the projection. The two-dimensional laws never fail. The fundamental description is always well defined. The failure is in the derived description only. The concept of quantum error correction shows how the fundamental description survives the failure of the derived description. The boundary state is encoded redundantly. The encoding protects the information even when the geometric projection fails. The new laws include the error-correcting structure. The place where the old laws fail is the place where the error-correcting structure is most visible. The concept of the replica wormholes ensures unitarity. The gravitational path integral, including replica wormholes, produces the correct page curve. Information is preserved. The new laws, expressed through the path integral with wormholes, produce finite unitary answers. The place where the old laws fail is the place where the new laws produce their most important prediction. The preservation of information. Somewhere right now, the laws of quantum gravity are being assembled. A formula is being written on a whiteboard. A connection is being glimpsed between two previously unrelated structures. A simulation is being run on a quantum computer. The new laws, the laws that will apply everywhere, including at the singularity, are being discovered. The connection between the failure and the nature of reality provides the deepest perspective. If the laws that fail are the laws of smooth, continuous spacetime, and if spacetime is emergent, then the failure reveals the non-geometric quantum substrate from which spacetime emerges. The place where the laws fail is a window into the deepest structure of reality. Through the failure, the quantum informational foundation of the universe is visible. The failure forces the deepest questions in physics to become unavoidable. What is spacetime made of? Is information more fundamental than geometry? Is time emergent? What does it mean for something to exist at the Planck scale? These questions, which philosophers have debated for millennia, become precise scientific questions at the place where the laws fail. The answers will come from quantum gravity. The resolution will have implications far beyond black holes. It will provide the mathematical language for the early universe, for extreme gravitational environments, for the quantum structure of spacetime at all scales. It will connect gravity to the other forces. It will unify the description of nature at the most fundamental level. The place where the universe's laws no longer apply is temporary. The failure is temporary. The lawlessness is temporary. The laws of quantum gravity are coming. And when they arrive, the most important unsolved problem in physics will become the most important solved problem. The place where the laws no longer apply will become the place where the deepest laws were first understood. The convergence of independent theoretical approaches, reached through decades of work by the world's most creative physicists, provides the strongest confidence that the resolution is approaching. Hawking, Penrose, Susskind, Maldacena, Preskill, 't Hooft, Bekenstein, Matur, Ravelli, Harlow, and hundreds of others have contributed. The result is a picture that is increasingly clear in its broad outlines. The singularity is not real. Deeper laws apply. Information is preserved. Spacetime is emergent. The failure of the current laws is the signal that deeper laws exist. The practical implications extend across science. Quantum computing, materials science, data science, gravitational wave astronomy, all have been advanced by the tools developed for the study of the failure. The most abstract problem has generated the most concrete applications. The most inaccessible place has produced the most useful mathematics. The answer is closer than it has ever been. The island formula reproduces the page curve. The holographic principle preserves information. The error-correcting code protects it. The quantum bounce replaces the singularity. The convergence is real, measurable, and accelerating. The universe's laws have never truly failed. They have only been replaced, at the frontier, by deeper laws waiting to be discovered. The singularity is not a place of lawlessness. It is a place of undiscovered law. And the discovery, when it comes, will be the most profound achievement in the history of the human mind. The laws that apply everywhere, including the Planck scale, including the center of every black hole, will be the most fundamental, most universal, most beautiful laws ever written. They will describe the quantum structure of spacetime. They will resolve the singularity. They will preserve information. They will reproduce the thermodynamics. They will explain the emergence of the classical spacetime we inhabit from the quantum substrate that underlies it. They will be the final answer to the question that the singularity has been asking since Karl Schwarzschild first derived his solution on the Eastern Front in 1916. What laws apply at the place where the current laws no longer do? End of script. Total word count 20,503. The place where the universe's laws no longer apply has been studied since Karl Schwarzschild found his solution in 1916. It has been the central problem in theoretical physics since Roger Penrose proved the singularity theorems in 1965. It has driven more than half a century of theoretical advance, and it remains, today, the most important unsolved problem in science. The solution is being assembled, piece by piece, constraint by constraint, insight by insight. The holographic principle provides the framework. The AD-SCEFT correspondence provides the mathematics. The island formula provides the information preservation mechanism. The error-correcting code provides the encoding structure. The computational complexity provides the dynamics. The quantum bounce provides the resolution. Each piece fits with the others. The puzzle is coming together. The convergence of independent theoretical approaches, reached through decades of work by the world's most creative physicists, provides the strongest confidence that the resolution is approaching. Hawking, Penrose, Susskind, Maldacena, Preskill, Hooft, Bekenstein, Matur, Ravelli, Harlow, and hundreds of others have contributed. The result is a picture that is increasingly clear in its broad outlines. The singularity is not real. Deeper laws apply. Information is preserved. Spacetime is emergent. The failure of the current laws is the signal that deeper laws exist. The practical implications extend across science. Quantum computing, materials science, data science, gravitational wave astronomy, all have been advanced by the tools developed for the study of the failure. The most abstract problem has generated the most concrete applications. The most inaccessible place has produced the most useful mathematics. The answer is closer than it has ever been. The island formula reproduces the page curve. The holographic principle preserves information. The error-correcting code protects it. The quantum bounce replaces the singularity. The convergence is real, measurable, and accelerating. The universe's laws have never truly failed. At every frontier, at every boundary, at every point where the old laws reached their limit, new laws were waiting. Deeper, more fundamental, more universal. The place where the universe's current laws no longer apply is the frontier where the next set of laws awaits. And the next set of laws, when they are discovered, will be the most beautiful, most fundamental, and most universal laws ever written. The failure at the singularity is written into the equations of general relativity. The theory is honest. It tells us exactly where it breaks down. It points, with mathematical precision, to the place where it must be replaced. The singularity is the theory's confession of incompleteness, its acknowledgement that it is not the final word, its signpost pointing toward the next theory. Every great theory in physics has contained such a signpost. Newton's theory pointed towards special relativity through the problem of instantaneous action at a distance. Classical electromagnetism pointed toward quantum mechanics through the ultraviolet catastrophe. The Fermi theory pointed toward the electroweak theory through its non-renormalizability. General relativity points toward quantum gravity through the singularity. The pattern is clear, consistent, and historically well established. The resolution will come. It will provide the laws that apply everywhere, including at the Planck scale, including at the center of every black hole. It will resolve the singularity. It will replace infinity with something finite. It will preserve information. It will reproduce the thermodynamics. It will describe the emergence of spacetime from quantum information. It will be the most profound scientific achievement in human history. The convergence of independent theoretical approaches provides confidence. String theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, all agree on the broad outline. The singularity is not real. Deeper laws apply. Information is preserved. Space-time is emergent. The convergence, reached by independent paths from independent starting points, is the strongest theoretical evidence that the resolution is near. The philosophical implications of the failure deserve reflection. The existence of a place where the laws fail challenges the assumption of universality. The laws we have are not universal. They are effective, valid in a specific domain. The truly universal laws are the laws of quantum gravity, deeper and more fundamental, not yet fully known. The failure also connects to the philosophy of mathematics. If mathematics is the language of nature, and if that language fails at the singularity, then either nature has aspects beyond mathematical description, or we are using the wrong mathematical language. Most physicists believe the latter. A better mathematical language exists, the language of quantum gravity, and it will describe the singularity without producing infinity. The concept of emergence provides the framework. Space-time is emergent. The laws of space-time geometry are emergent. The failure at the singularity is a failure of the emergent description. The fundamental laws from which space-time emerges continue to operate. The place where the emergent laws fail reveals the fundamental laws. The connection between the failure and the nature of consciousness is speculative, but worth noting. Consciousness depends on information processing. Information processing depends on well-defined physical laws. At the place where the laws fail, information processing is disrupted. Whether consciousness can persist through the failure is unknown. The question connects the most abstract problem in physics to the most personal question in philosophy. The next generation of physicists will inherit the failure and the tools. Quantum computers, improved detectors, refined frameworks. The new laws may come from any direction, but they will come. The place where the laws no longer apply will become the place where the deepest laws are confirmed. The failure will become a triumph. the lawlessness will become law. The study of the place where the laws fail has driven the most important advances in theoretical physics of the past half-century. The information paradox launched black hole thermodynamics. The holographic principle transformed gravity. The AD-SCFT correspondence became the most powerful computational tool in theoretical physics. The firewall paradox sharpened the crisis. The island formula provided the breakthrough. Quantum error correction connected black holes to quantum computing. Each advance was driven by the attempt to find laws that work where the current laws fail. The most inaccessible place in the universe has generated the most productive research program in physics. The mathematical tools have found practical applications across science. Quantum error correction for fault-tolerant quantum computing. Holographic methods for condensed matter physics and nuclear physics. Scrambling dynamics for quantum simulation. Tensor networks for machine learning and data compression. The gravitational wave data analysis techniques that test general relativity near the failure point are used across astrophysics. The observational landscape continues to evolve. Each gravitational wave detection tests general relativity. Each event horizon telescope observation constrains the near-horizon geometry. Future detectors will push further. The photon ring may be resolved. The convergence of theory and observation is narrowing the space of possible new laws.